Alright guys, this is the vector test review that was requested by students. I guess they have a test coming up. Line L1, okay, this is number 1 here. Line L1 is represented by R1, and this is a point vector plus a scalar times a direction vector. So we have line 1 and line 2, and there's another point vector and another direction vector. Apparently these lines will intersect. Let's find the point of intersection. Okay, so what we're going to do is take this vector equation of a line and set it equal to this vector equation of a line, and where they equal, that's where they should intersect. So I have 2 plus s times 1. So 2 plus s. And that's going to equal negative 3 plus t times negative 1. I'm sorry, 3 plus negative 1 times t. So it's 3 minus t. We got 5 plus 2 times s. It's the second equation. This is a 5. Can't draw that very well. Ooh, that looks terrible. And this is going to be negative 3 plus 3t. Alrighty. So I'm going to solve this system of equations, and you can do this by hand if you like, or you can go ahead and quickly use the calculator. So that's what I'm actually going to do. So in my calculator window, I'm going to go to Menu, Algebra, Solve System of two equations. I'm going to change the variables to s and t instead of actually solving it. Alright, so I'm going to type in these equations. Let's take a quick look at what they were. Let's see, this was 2 plus s equals 3 minus t. And the other, five plus 2s equals negative 3 plus 3t. So 5 plus 2s equals negative 3 plus 3t. So I type in my system of equations, I hit enter, and it's going to give me the values of s and t. So s is negative 1 and t is 2. Very well, so we come back to this question here, and now that I know that s is negative 1, we can write this here. It's a negative 1, and t is in fact 2. Then I can make this negative 1, or I can make this 2. It doesn't make any difference, but I just need to get points out of these vector equations. So let's say this is equal to 3 plus 2 times negative 1, or 3 minus 2, which is 1. Negative 3 plus 2 times 3, or negative 3 plus 6, which is 3. And then we got 8 plus 2 times negative 4, which is 8 minus 8, which is in fact 0. This is actually the coordinates of t where they intersect. So we could say t is given by the vector coordinates of 1, 3, 0. This is the position vector of t, where the two lines will intersect. So that's okay. That's the answer for that one. So let's go further down here. Let's go on to the next question. Okay, we got this second question. The position vector of A is this, and the position vector of B is this. Show that the vector AB is this. Okay, so vector AB is given by the position vector of B minus the position vector of A. So B is going to be 4, negative 5, and 21. Write this as a matrix, negative 5, 21. And I'll subtract the position vector of A over here, which is 2, 3, and 1. 2, 3, 1. 4 minus 2 is 2. Negative 5 minus 3 is negative 8. And 21 minus 1 is 20. So as you can see, 2, negative 8, 20 match these terms here, 2, negative 8, and 20. These components. So it is shown. This is done. No problem. Find the unit vector u in the direction of AB. If you recall, to find a unit vector in the direction of AB, this is kind of what's happening here. I have a point A and this is a vector traveling from point A to point B. And I want a unit vector, which is right here, that's not near as long, just 1 unit long, as opposed to the magnitude of AB itself. So to get this unit vector, what I'm going to do is actually take the vector AB, which I have, and then divide every one of its components by the magnitude of AB. Okay, so the first thing I have to do is find the magnitude of AB. So the magnitude of AB we can find using the distance formula. So it's going to be the square root of 2 squared plus negative 8 squared plus 20 squared. Alright, so let's take a look at this. It's going to be 2 squared plus negative 8 squared plus 20 squared. Alright, and this is going to be 4 and 64, which is going to be 68, and then 20 squared is 20 times 20, so that's going to be 400. So this will be 468, square root of 468. Okay. Now what I have to do is divide every one of these components of AB by root 468. So that's what I'm going to do here. So the vector U, which is the unit vector they're talking about right here, is going to be given by 2 divided by root 468. And that'll be your I component. And then plus, what we're going to have is a negative 8 divided by root 468. That would be your J component. And then plus 20 divided by root 468. And that will be your K component. And that technically is your answer for the unit vector. It's this. This is the unit vector. It's all equal to everything there. So it's not a pretty answer, but that's what it is. We want us to show that this vector we just created is perpendicular to OA. Now keep in mind that OA is the same vector as the point vector A. So it's this right here. This is OA. To show that if two vectors are perpendicular, that means their dot product or scalar product has to equal 0. So I'm going to take the scalar product of this vector right here and this vector right here. So let's take a look at that. So we're going to say U dot product with OA is going to equal 2 times this right here. So I'm going to get 2 times 2 on the top here, which is going to be 4 over root 468. Okay. And then I'm going to add 3 up here, 3 times negative 8 here, so this is going to be negative 24. That's a 4 over root 468. And then plus, this will be 1 times 20 right here. What's it, just 20 over root 468. And this will be your other term here. So I know that 4 plus negative 24 is negative 20. This plus this is negative 20 over root 468. And I add that to 20 over root 468, and that's going to give me, in fact, 0. That's actually true. So because this dot product is equal to 0, it is now showing that the unit vector we found is perpendicular to OA. That is actually true. All right, so we're going to go on to the next question. That's about all you have to show. All right. It says, let S be the midpoint of AB. The line L1 passes through S and is parallel to OA. And they want the position vector of S. So S is at the midpoint of AB. All right. So I'm having difficulty here. Let's do this. Every time I click on this, it just jumps. It's not supposed to do that. All right. Okay, so if we want the midpoint of AB, we're going to use the midpoint formula. So we take A and we take B and we'll find the midpoint. So I'm going to add every component. So 2 plus 4. I'm going to add the x components and I'm going to divide by 2. So 2 plus 4 will be 6, and that divided by 2 will be 3. And that's how we're going to do this for all the points here. So it's going to leave some space so we can go back and see it here. So I'm going to come down here with this, with my pen here, and I'm going to say then we're going to have 2 plus 4, which is 6, divided by 2, which is 3. 3, that'll be 3i. I got 3 right here, plus negative 5, that's going to be negative 2, and we're going to divide that by 2, and that's going to be negative 1, so minus 1j. And then I'm going to have 1 plus 21, which is 22, divide that by 2, which is 11. So this will be 11k. This is actually the vector equation for S. This is it right here. It's 3, negative 1, and 11. That's the actual components of the position vector for S. This is correct. Okay. Now they want me to go a step further here. Write down the equation of L1. They've told me that L1 passes through S and is parallel to OA. Alrighty, so that's useful information for me, because now what I'm going to do is keep in mind that I'm asking to write down the equation of a line, the vector equation of a line. So a line, L1, is given by a point vector plus some sort of scalar, which I could call P, I guess, right, times a directional vector. So this point vector is a point on the line, and since we know it passes through S, we'll use this point S as our point. So 3, negative 1, and 11. 3, negative 1, 11. Okay, the directional vector, since it's parallel to OA, it actually has the same direction as OA. OA is parallel to itself in terms of vectors, so we know that OA is actually the same thing as the vector point A by itself anyway, so it's going to be 2, 3, and 1 right here. There's a lot going on here, so let's just keep moving. So that's the answer for that one. Line 2 is given by this vector equation. So remember, you have a point vector right here and then a scalar times a directional vector. And they say that this line right here, L1, and this line L2 are in fact what? They want me to explain why they are not parallel. If they were parallel, their directional vectors, so I'm talking about this vector right here and this vector right here, would have to be scalar multiples of each other. Okay, so I take a look at this first number 2, and I say, okay, what do I multiply 2 by to get this negative 2 over here? That means P would actually have to be negative 1. Okay, I'd be saying that P is in fact negative 1. So negative 1 times 2 is negative 2. But negative 1 times 3 is not 5. It's actually negative 3. So these obviously are not scalar multiples. As a result, here's the explanation of why these two lines are not parallel. Their direction vectors are not scalar multiples of each other. And because of that, they cannot be parallel. They have to intersect at some point. Alright. So, of course, the follow-up is, oh yeah, lines L1 and L2 in fact do intersect at point P. What is the position vector of P? Okay, so now I'm going to have to take this equation right here for L2 and this equation for L1 and set them equal to each other to figure out where they cross, where they intersect. So we're going to say 3 plus P times 2. 3 plus P times 2. So 3 plus 2P is going to equal 5. Okay. 5 plus what? Plus S times negative 2. So 5 minus 2S. I need one more equation to solve for the two unknowns P and S. So we're going to try this. Negative 1 plus 3 times P, which is negative 1 plus 3P. And this will equal 10 plus S times 5. So 10 plus 5S. And now I can solve this. I'm actually going to try to solve this by hand instead of using the calculator because I don't want to toggle back and forth here. So what I'm going to do is this. I'm actually going to solve this top equation for P. So I'm going to add 3 to both sides and divide everything by 2. Actually, tell you what, I'm not going to do that. I want to solve this using elimination. That would be easier. Let me extend this page here. This is what I'm going to do. I'm going to multiply this top equation by 3 and this bottom equation by negative 2. I'm going to eliminate. This will be easier, I believe. So we'll say 3 times 3 is 9. 3 times 2p is 6p. 3 times 5 is 15. And then 3 times negative 2s is negative 6s. Negative 2 times negative 1 is 2. We got negative 2 times 3p, which is negative 6p. We got negative 2 times 10, which is negative 20. So negative 20. And then negative 2 times 5, which is negative 10s. And then we add these two equations together. 9 plus 2 is 11. 6 minus 6p, these are gone, eliminated. 15 minus negative 20, or sorry, 15 minus 20 is negative 5. And negative 6s minus 10s is, in fact, negative 16. Negative 16s. I will add 5 to both sides of this equation. So give me 0. This will give me 16. So 16 is equal to negative 16s. Divide both sides by 16. S is equal to negative 1. That's not the answer, but we're almost there. Okay, so now all I have to do is plug in negative 1 for this s right here, and then distribute it into this vector, add it to this vector, and I can get 3 points out of this. So we're going to say, all right, if I have 5 plus negative 1 times negative 2, that's the same thing as 5 plus 2, so that first component will be 7. 10 plus negative 1 times 5 is 10 minus 5, so that's 5. 10 plus negative 1 times negative 3 is 10 plus 3, so that'll be 13. Okie doke. So what that's telling me is that this answer is 7, 5, 13. And that would be the position vector of P, where these two guys actually cross. So we can say this is equal to P, basically. That's your answer, position vector, where they intersect. Alright, that's that. Okay, number 3. Show that vector AB is this. Remember, to find AB, we'll just simply take the point vector for B and subtract it from A. I'm sorry, subtract A from that. So B, they tell me, is negative 3, 4, and 2. I'll subtract A, which is 1, negative 2, and 3. I'll get negative 3 minus 1, which is in fact negative 4. 4 minus negative 2. This is actually negative 4. This is terrible. Negative 4. And then we got 4 minus negative 2, which is 6. And then 2 minus 3, which is negative 1. So this is negative 4, 6, and negative 1. This is identical to this. It's supposed to be. Okie doke. So find the angle BAO. Now keep in mind, if I had points at B, another point at A, and another point at O, I would have BAO. And I want this angle here, right here, on A. So what I'm going to imagine is a vector leaving A toward B and a vector leaving A toward O. So these vectors are leaving the angle point right here. And I want to figure out what this angle is. So I need the vector from A to B, which is AB, which is nice because I have it right here. And then I need the vector AO. Now this is actually the point A, so it's the vector equation of OA. So to get AO, I'll just take all these numbers and flip their signs. So what I'm going to now declare then is that AB is of course negative 4, 6, and negative 1, because it's given to us right here. And I know that AO is the opposite of all these, so negative 1, 2, and negative 3. And now to find the angle between these two vectors, I'll take the dot product. So I'll take the dot product of these two vectors. So the dot product of AB and AO is given by negative 4 times negative 1, which is 4, plus 6 times 2, which is 12, plus -1 times -3, which is 3. So that's 12 and 7, so this will equal 19. The dot product of these two vectors is a positive number, so the angle between them is an acute angle. Alright, now keep in mind we know the formula for a dot product of two vectors is equal to the magnitudes of these two vectors, the product of these magnitudes times the cosine of the angle between them. I have now just found this part right here. I know this part right here is 19. I found it. So this is 19. Now I have to find the magnitudes of these two vectors, a and b. So now I have to find the magnitude of AB. How do you do that? Well, the magnitude of AB is given by taking the square root of every term squared. -4 squared plus 6 squared plus -1 squared. So much writing. And we'll figure this out. So this is 36 and 16. So that, what is that? 36 and 16. 46, 52. Okay. And then plus 1. So this will be root 53. This one right here, the magnitude of this one, this will be 9. We'll square all these terms, so it'll be 9 and 4 and 1. So that'll be root 14. So what I'm basically saying is that the magnitude of one of these is root 53, and the magnitude of the other is root 14, and this is times the cosine of the angle between them. So theta, the angle that I'm after, which is the same thing as VAO, that angle, is going to be given by the cosine inverse of 19 over root 53 times root 14. And then we use the calculator to figure out the rest. So this angle theta is going to equal, cosine inverse, control divide, I'm going to put 19 on top, and then it'll be root 53 times root 14. This angle is 45.8 degrees about. So let's go back to your problem. And we'll say this answer is 45.8 degrees. And that's your answer for the angle BAO. Alrighty. Moving on. Alright, line L1 has this equation. Write down the coordinates of 2 points on L1. Well, that's easy. All I have to do is change the scalar to different numbers. So the first number I'll use for S is 0. So if I make this S0, it's 0 times all of this vector. If that's the case, then one point I'll have is this vector plus 0 is -3, 4, and 2. It'll stay the same as -3, 4, and 2. So that will be one vector. And then I'll say another point is if I make S a 1. So if I say -3 plus 1 times -4, that's going to be what? -3 plus -4, which is -7. 4 plus 6, which is 10. And then 2 plus -1, which is 1. So these are in fact two different points on L1. All you do to get points is change the value of S to something else. And that'll give you infinite many points if you keep changing S. Alright, now we're on on part C here. Okay, it says the line L2 passes through A and is parallel to OB. Find a vector equation L2, giving your answer in the form R equals A plus T times B. Okie doke. So R is just a vector, which we call XYZ, at some point on a line. And right here is A, which is another point vector. And this is going to give you a point on the line here. That's probably going to be point A because L2 passes through point A. And then we're going to add a scalar, which is T, times the directional vector. Okay, times the directional vector B. So what I'm going to say now is B is the same thing as OB because OB is parallel to L2, which means they have the same directional vector, being OB. So let's figure out what point A is. I'm going to come up here and I'm going to see that the coordinates for point A is 1, -2, and 3. So let's go ahead and write that in. It's going to be 1, -2, and 3. I need the vector equation for OB, which is actually the same thing as the point vector B itself, and I'm going to put that in my directional vector. Alright, so here's B, which is -3, 4, and 2. Alright, -3, 4, and 2. Very well. And now I'm going to try to solve this problem. So this next problem, they tell me it's point C. Point C is on L2. So we can substitute point C for this vector right here and set it equal to the vector equation of the line and figure out the coordinates of C. So instead of x, y, z, I have k, -k, and 5. So let's try that. K, -k, and 5. This will equal this point vector 1, -2, 3. Plus t times this vector, -3, 4, and 2. And looking at this, I can see 5 is equal to 3 plus 2 times t. So 5 is equal to 3 plus 2t. If I subtract 3 from both sides, I can see that 2t is equal to 2, and therefore t must be equal to 1. So now I think this t is equal to 1 here. Alright? And now I can figure out what k is. K is equal to 1 plus 1 minus, 1 plus 1 times -3. So basically it's equal to 1 minus 3, which means k is in fact equal to -2. If that's the case, then -k is equal to +2, and I've actually discovered my point C here. This is my point C, and I know that C is equal to k, which I now know to be -2 right here, and then the negative of that for the next one, the -k, which is now +2, and then 5 will be the last one. So this is the actual point C that we wanted, and that's the coordinates that they're asking you for. Fine, that's that answer. Alright, we keep going.